Yeah, so V2 to ground, and next V2 to ground, so that 2 0 over 3. And then 2 minus 4 over
Good, good. How about you?
that resistor, and then
Good.
V3 to ground. So V3 over 3. And then I think this is my last
I don't know where one is.
14 equals V2
No, it's
yeah, it's V1 over 2.
it's on both PCs.
But yeah, that's 4 equation. Really 3 equations, 3 unknowns. You got V4, right?
Yeah, that's what
Yeah, that's the one that you
it has like
that's us. That's what after that.
like
I think I put everything into this equation, and I put everything there with V2, and it's pretty nice.
So I had a tablet.
You know where V4 is, and then just solve it.
This is a lot.
And then you can get V1.
Okay, thank you for showing up despite a vicious snowstorm that we had last night. So, a small thing for you, right? You must be from North Dakota, right?
I'm from Bulgaria.
Bulgaria. Okay. Okay, are there any questions before we get started? Okay.
I actually have a question.
Yes.
For the homework on the last one with the complex numbers, I had a question about, so e to the pi j, isn't that just -1?
Yeah.
If you, so when I reduced, I switched everything to polar from rectangular, and then I divided them first. But I was curious because it would give me a different angle if I just did e to the pi j was -1 and just turn that into a -1 out front instead of dividing subtracting the exponents by dividing the e's. If that makes sense, like it'd give me a different angle.
Your mathematics has to be consistent. So if you do it two ways and it's not consistent, you probably have made an error somewhere.
Right.
So
Okay.
you should go back and check your error.
Okay.
You can do it in polar form, you can do it in Cartesian form. Mathematics is very logical. So the two answers have to be consistent. So that's a good check for your method.
Right,
If they
so
don't
I'm doing
agree,
something wrong.
something is wrong.
Okay.
Go back to the drawing board and check again. Okay? Something is wrong somewhere.
No, you need to take care of the magnitude because -1 will again go up on the exponent, right? So there will be a plus pi in your exponent angle.
I'll ask you after class.
Okay. Okay. So today we're going to start on the new topic called op-amps. Okay, this stands for operational amplifiers. These are nifty devices actually that help you simplify electronic circuit design. And they're like black boxes, but you don't have to understand how it works in detail, but just how it looks like from the external view. So you treat this as a black box, and if I were to draw the picture of an op-amp, it's usually replaced with a triangle. And then it has two inputs. Okay. The first input we call it V plus, and then the second input we call it V minus. And then the current that goes into the first terminal we call I plus, and the current that goes into the second terminal we call I minus. Okay, this is the input to an op-amp. And then it has an output. Okay, output over here. And then we call the output voltage VO. And there is an external current that you can also draw from this op-amp. And it's called I/O. Okay, but there are lots of electronic gadgetry that goes into this thing. Okay, so it has to be actually biased by an external voltage in its actual application. And then we can say that been biased in this manner, so that there's a ground over here, and this is VB over here, and then there's another biasing called the VB on this thing. Okay? So this is VB over here, this is minus VB at this terminal because of this biasing effect. But usually we just ignore this external biasing circuit. It is necessary to get the op-amp to work, and we just worry about this triangle. So there is quite a bit of gadgetry. And then quite a bit of clever electronic engineering, so we call it wizardry. Okay, that you don't have to worry about. You just have to worry about how it works in the outside, or from the outside. Okay? So, if we were to plot VO versus the input is actually always coming together as V plus minus V minus, and VO being the output. It is an amplifier, so for a very small voltage, you get a rather large voltage over here, okay, because it's a kind of an amplifier. So you can say that the op-amp works almost like this. This slope is very, very steep actually, but because in order for me to draw it so that you can see and give it a finite slope, its slope is almost vertical, okay? And that it saturates after a while. If the input is too large, it saturates. So actually it goes like that, but we can approximate the curve with a straight line in this manner. Okay? And then there is a value here called VB, I believe. V0 equal to VB. VB being the saturation voltage. You can never have VO larger than VB. Okay, this operational amplifier. And hence you can say that this is VB over A. Because this slope is very, very steep. Okay, the slope is very, very steep. A is much, much larger than 1. The slope of this line is A, as you can see. Okay, the slope of that line is A. A is much, much larger than 1. And that if you were to input this differential voltage, this is usually called a differential voltage, in the negative direction, you go to minus VB, let me call this differential voltage. Or differential input voltage. Okay, it will operate in this manner, but you also go to saturation if you do too much in the other direction, and this value here is VB over A. Okay. You can imagine that this number is actually a very small number. VB over A is actually a very small number because this slope is extremely steep. Okay. So, yes? A is an amplification factor, and A is a number that is very large. A could be typically, say, 10 to the 6. Okay, so it's large. It is a large number. If I were to draw it to scale, you cannot see this diagram very well. It's an extremely steep slope. Okay? So you know what A is now? It's just a number. Amplification factor.
Defined by the optical amplifiers?
Not optical amplifier, operational amplifier.
Oh,
I wrote operational amplifier here, not optical. Okay? So please distinguish the two. So it is according to the amplifier that you have bought, and you pay your money for it. I guess the more expensive it is, the larger A would be. If you buy a crummy one, A would be very small, and that's not very good, right?
Can we get a cheap one and just fix it ourselves?
Well, if you're, I don't think so. Things are so minuscule these days that even when you open them up, they are probably full of nanotechnology and micro technology, and you cannot do it at home anymore. You have to consign this to some shop somewhere in California to do it for you. Okay. So things are that way now. No more homegrown electronic hobbies. Okay? Not like maybe 10, 20 years ago. So because of its behavior, you have something, an equivalent circuit that looks something like this. I plus, I minus. Okay, I can have an equivalent circuit that looks something like this to describe this amplifier. And I have the voltage control voltage source whose voltage amplitude is proportional to A times V plus minus V minus on this side. And then this could be grounded. Okay, and then you have something like V naught and I naught over here. Okay, and then I naught. I naught can be coming out here. And then this could be the internal resistance of this op-amp. Okay, this is the output resistance of this op-amp. This is the internal resistance of this op-amp. The good thing about op-amps is that Ri is very, very large. Ri is typically very, very large and Ro is very small. Okay, so you can say that Ri usually much larger than Ro. Okay, that's one fact that you should know. And that you can think of VO being like a Thevenin equivalent. So it consists of a voltage source inside, which is a control voltage source minus the Thevenin resistor times the output current. So VO can be approximated by this formula, and RO is the output resistance, and then Ri is the input resistance. Okay? And typical values is that RO is about 1 to 10 ohms. Just 1 to 10 ohms. So it's not too bad, it's small. But Ri is typically on the order of 10 to the 6 ohms. So when it's 10 to the 6 ohms, what do we call it? Mega ohms. Okay, this is in terms of mega ohms. Okay? And then A is an amplification factor that is on the order of 1,000,000. Okay, so it's rather large. And typically, V plus minus V minus is very small. It's typically on the order of 10 microvolts. Okay, because you just need a very small voltage over here. Okay, V plus, V minus. And this amplification factor is going to blow it up. So you don't need a lot of voltage in here. And then you can give rise to a current. Okay, what is the good thing about an op-amp? The good thing about an op-amp is that for a guy looking from this way, he only sees this part of the circuit. He sees a circuit with very low internal resistance. Okay, voltage source somewhere in there, but the internal resistance is very small. What is good for a voltage source with very little internal resistance? Yes?
High current.
High current is good, that its voltage will not be affected. If you were to hook a load to a voltage source, let me draw the same source as I had in the diagram. If you have such a kind of a circuit configuration, if you were to change your RL, okay, the voltage that this thing sees is very much this voltage. Say this is the voltage source that you see. The voltage across here is typically Vs also because of the voltage divider. And if RL is much, much larger than RO. But if RO is small and you hook a load that is much larger than RO because of the voltage divider formula, you can see that V out here, okay, V out is typically equal to RL over R0 plus RL times Vs. Vs is given by this thing over here. Okay, so it's not affected by external loading. The voltage is not affected so much by external loading. Whereas if you have a bad voltage source, the voltage that you get out of the voltage source very much depends on what resistance you hook onto the voltage source. Okay, because of the internal resistance being small, you can hook any resistance to it, not affecting the voltage source. Of course, there would be a saturation of the current. We cannot draw infinite current from this because this was saturated amplifier. You go into the saturation mode. But the good thing is that it is not susceptible to external loading. Okay, and typically V plus minus V minus is less than VB over A. Okay, we operate in this range. We operate in this range. If you operate in a linear range where the amplifier is not saturated, then the differential voltage satisfies this relationship. Okay? Are there any questions so far? Because of this very peculiar way the thing is constructed with this very, very large A, we can make approximation to this circuit. The approximation that we can make are called op-amp approximations. And you better commit this to memory. Okay, these are very important. And that V plus is approximately equal to V minus. Because this difference is so small in terms of microvolts. Okay, you just need a little bit of differential voltage. You can get something going. Okay, I plus is typically 0. Okay, I plus is typically 0 is because Ri is very, very large. Ri is on the order of mega ohms. Okay, Ri is on the order of mega ohms. So you just need a little bit of current to put into this circuit, and it works. Okay, I plus is typically 0. And then I minus is also typically 0 because they're just next to each other. Okay, they are very much about equal to each other. And they are on the order of picoamps. Picoamps, okay? And this is on the order of microvolts. So that is the op-amp, the summary of its behavior. So far, are there any questions? If not, let's see what we can do with it. One very simple thing we can do with it is to design a voltage follower. Okay, what is a voltage follower? You make a voltage follower in this manner. You have an op-amp. Let's ignore the biasing voltages. Okay, that you have an output VO, IO coming out. And then you have differential currents and differential voltage going in. V plus, I plus. And then you have V minus. And then you hook it in this manner. And so this is I minus. This will be I minus 2. Okay? And then you let this be an external terminal. And then you hook a source resistance to your driving voltage source. I'm going to argue that V0 is going to be approximately equal to Vs. And then to convince you that this is a fact. V0 will follow the source voltage Vs to very high precision, to within microvolts. Okay? So let's see how this comes about. Say, let's assume that V0 is equal to Vs minus delta, where delta is a positive number. Delta being a positive number. So let's assume that V0 is equal to that. Then from this picture over here, you see that Vs or V minus is equal to V0 is equal to Vs minus delta. Okay. I plus is a very small current. I plus is a very small current. So how can I approximate V plus? If I plus being a very small current, because this thing has very huge internal resistance, okay, what do you think I plus should be? Very small, right? And what should V plus be equal to?
Yes.
V plus should be equal to Vs, right? Because the voltage drop across this would be very, very small. Because I plus is actually something in terms of picoamps. Okay, it's extremely small number. So V plus is going to be Vs, but I just convince you that V plus and V minus are very close to each other. Okay, which means that Vs is going to be equal to V minus, which means that delta must be a very small number. So if I look at V plus minus V minus, okay, it will be approximately equal to Vs. V plus is approximately equal to Vs minus Vs minus delta. Okay, that is the differential voltage, and if you work it out, it will be delta. But V plus minus V minus is a very small number, so delta must be a very small number. So VO is just a shade, a tiny shade different from Vs. This delta is a very small number. Okay, delta is on the order of microvolts. Okay, it's on the order of microvolts. Okay, so this is called a voltage follower because VO will be approximately equal to Vs in this diagram. What is good about this way of configuring the source? The good thing about this way of configuring the source is that it is not subject and susceptible to external loading. You can put a load over here, you can connect this to a load, and that load is not going to change the internal resistance very much. As I said before, that load sees a very small internal resistance, whereas if you were to hook this load directly to this source configuration, okay, it's going to be altered due to the fact that RS might not be much smaller than RL. Okay, external loading will change the voltage. So this is called buffering. This effect of protecting the source voltage from the loading from the external source with this very complicated electronic system is called buffering. Okay, we can call this buffer. A protection. Buffer is like protecting, right? Provide a buffer zone in a war. Provide a protection zone. Okay. And then you can also make the op-amp into an amplifier very easily. And I just show how you can do that by designing a non-inverting amplifier. Let's see how we can do that. So it actually has an internal amplifier to it. So with clever electronic design, we can make it into an amplifier whose amplification factor or the gain can be controlled by external circuitry or external circuit design. So the way to design a non-inverting amplifier is this way. And then V minus. And then instead of hooking this to directly through the output terminal, I have a voltage divider here. Okay, I have a voltage divider circuit, and this is connected to ground. And then I put in my driving source in this manner. Okay, this is still my R source, and I call this R1, R2, and this is still my VO, this is my IO. Okay. So if I look at this design now, this thing draws very little current. I minus is very, very small. So this is almost like an open circuit. Okay, this is almost like an open circuit. And what is the voltage at this point? Immediately you can conclude what the voltage at that point is. If you know that this is VO, okay, say VA, VA must be equal to something times VO, a voltage divider formula times VO. What should VA be? If this is 0 volt, down at the ground here, this is VO volt. Yes, somebody wants to? R2, what else? Over R1 plus R2, right? This is a voltage divider formula. So that is VA, and this must be V minus. Okay, V and V minus are connected by a short circuit. But in an op-amp, V plus is approximately equal to V minus, because this differential voltage is extremely small. But V plus is approximately equal to Vs, because this input current is very small. There's almost no voltage drop across the Rs. Okay? Then you see that VO is equal to R1 plus R2 over R2 times V minus, okay, times Vs. Because this is V minus, if you use this formula, you get this formula, and then you get this being equal to that, and this is equal to V minus. Okay, so you plug this in there, you get that the output voltage is equal to 1 plus R1 over R2 times Vs. Okay, this is usually called the gain of the amplifier, the gain times Vs. So you can design a voltage amplifier by just this design, and that you can change the resistors. The smaller you make R2, the larger the gain would be. Okay, this is the gain factor. So the smaller R2 is, the larger the gain factor would be. And you can change the amplification of this non-inverting amplifier by just changing the external resistance. So they are within your control. Okay, so this is a second use of the op-amp. And of course, as I said before, op-amps can be used for buffering. And when you use the op-amp for buffering, it protects your source and source resistance and voltage source from external loading. It's been protected by this very clever electronic circuitry here. So that was being discussed in the textbook. Whereas if I were to not have the op-amp and connect the source directly to the load, you will have this kind of configuration over here. And then Vs. Okay, this is a no buffering case. And then from this you can see that your VO, as I said before, is equal to RL over RL plus RS times Vs. And that's not good, because when RS and RL are of the same order, VO can change very much. But in this picture over here, RO is much, much smaller. RO is very, very much smaller. So if you do external loading, you don't get the voltage source being affected as much. Okay? So in fact, because of this voltage control source, that you actually find that the internal resistance is actually much, much smaller because of the voltage control source that you have over here. Okay, you find that as long as RL is much, much larger than RS over A, well, not RS over A, R0 over A, okay, that you can use the op-amp approximation, as long as this is true. And this is a big range because RO is not large. RO is on the order of ohms, 1 to 10 ohms. And then because of the amplification factor that you have over there, the internal resistance that you see is actually something more like this. You can actually work out the RT for this circuit. You find that RT is actually on the order of this. This is like your R7 for the circuit. And if you work that out, as long as your loading resistor is much larger than that number, the voltage is not going to change very much. Okay? But there's something that we work out later on. Something that we work out later on. We'll show that this to be the fact just in a little while. Maybe if not this lecture, the next lecture. Okay, that this fact is true. And let me see, I have maybe quite a bit of time left. Let me see what I can talk about. Let's talk about positive and negative feedback. You can also get the op-amp to work in the opposite direction, but it wouldn't work. Okay, there's a picture even in the textbook that if you were to put the op-amp in the negative feedback mode, it wouldn't work quite well. Okay, this is actually the positive feedback. This is called negative feedback. Okay, this mode is called the negative feedback mode. And then if you have a positive feedback mode, you hook the op-amp in this manner. You invert this two terminal and then put VO over here, and then you hook this to this positive terminal over here. And this wouldn't work. This wouldn't work for the reason that you easily would drive the amplifier into saturation. Okay, so this is a bad mode. Okay, this is no good. And you can argue yourself quite easily that if this is Vs, okay, let's assume that this is still Vs because of the low current approximation. Okay, that if V0 is Vs plus delta, okay, we want this voltage to be higher than that voltage over here. Then V plus will be equal to V0 plus delta. Okay? And then V minus is equal to Vs. And then you will have V plus minus V minus to be V0 is equal to Vs plus delta, okay? Vs plus delta, let's assume to be true. Then this will be in the delta value, okay? And then it turns out that delta can be anything and this will be satisfied. You can pick delta to be any value and you can put delta easily over here. You can put V plus minus V minus to be somewhere operating over here and delta can be here. And that equation can still be satisfied, and that clearly is no good. Okay, clearly it means that VO will be smaller than Vs. Okay, and you will give rise to a contradiction. Okay, so this kind of amplifier cannot work due to positive feedback, and it's explained in greater detail in the textbook. But let me not belabor on it further, but let's go on and do some more examples with this op-amp. So let me do example 3.1. And in this example, we hook up an op-amp in this manner. One side is a voltage follower. Okay, this is a voltage follower circuit. And this is V1, and this is RS1, and this is BS1. And then I have a resistor over here. Let me just erase this part of the blackboard.
Yeah.
And then I have an op-amp on this side. That looks something like this with a resistor, and then a VS2, RS2, and then this is a non-inverting amplifier configuration. Okay, I can connect this whole thing to ground. Okay, let's see how we analyze a circuit that looks something like this. And let's assume that this is 10 kilo ohms. This is 10 kilo ohms. And this is also 10 kilo ohms. And this is 20 kilo ohms. This is 10 kilo ohms, as is done in the example. Okay, and this is RS2. And then the first thing we like to do is to find out what V1 and V2 are. Okay, V1 must be equal to VS1. Because it's a voltage follower.